Welcome to week 8, internal forces. Now this one is going to be very interesting. We will be able to tell what's happening inside these rigid bodies, right? But before we get into that, we have to talk a little bit about the sign conventions and the type of forces we are going to find inside the members we are going to study, right? Which are called beams. Differently from a truss bar that can only carry compression or tension, now we'll have a few more forces to worry about, right? Now, up to this point, we have discussed external forces or loads that act on rigid bodies, and we learned how to find the external reactions on that body. And we did that by learning about supports and by applying our equilibrium equations to find the value of the reactions. But there is something, right, going on inside the member before the applied loads can get to the reactions, right? So how do the loads, the moment and the distributed load, right, in this case, right, how the loads in this figure, right, how the loads in this figure, let's mark them with blue. With blue, the loads, well, it's not very common, but, right, so I have these loads here, applied loads. How do the loads in the figure get from the point of application, right? The point of application in the case of the moment, or the area of application in the case of the load, to the reaction points that are marked by red, right? So how do these loads travel through the body, right? Through the body and reach the supports, right? How the support share the load. So what happens inside the member? So these are some of the questions that we are going to solve in the in this topic, right? So far we have taken a black box approach. We assume that the loads reach the reactions, but we haven't asked the question how, right? So, well, first of all, right, imagine that part of the structure, or perhaps all of it, is used to transfer the load from one location to the other, right? Now, there must be internal forces inside that are generated, right, within the rigid body. They carry the external load to the support, right? Now, the internal forces are the forces that individual molecules within the body actually feel when the load is applied, right? So it gives us an X-ray of what the rigid body is feeling, right? Even at the molecular level, right? It provides us with a window to see what's going on inside the rigid body. Now, why are these important? Well, the internal forces, right? Not the external forces, not the reactions, right? The internal forces, they dictate the size and shape and the material, right, of the cross-section of the rigid body. So if you want to use a bridge, right, if you're going to design a bridge to cross a river, in order to know how big you have to make it, right, and what shape are you going to make a bridge that has a rectangular cross-section, right, or circular, right, and what material, concrete, steel, aluminum, wood, right, you have to know the internal forces, right? So in the next courses of engineering, calculating the forces will be the first step, and then coming up with the geometry, right? Coming up with the geometry, the amount of material and the cost, right? These will be learned in future classes, right? But internal forces, you will learn it here. Now, the question is, how do we solve for those internal forces? I would say that actually the first question is, what are those internal forces? And then later, how can we calculate them, right? Now, in very advanced courses, right, one day, of course you will get there, you will be able to do these simulations you see on TV, in which a body is modeled in a computer, right? And the computer is given some instructions, and you are able to see how the forces and how the deformations of that body happen, right? So this is just a very, very simple example, right? This simple piece was modeled in the computer, right? The computer divided it into many small elements and applied some equations that that the computer knows, right? Well, you know, but the computer knows that the material behaves in this and this other way, right? And then it applied the loads, right? It applied the loads, and then the computer was able to get you the loads. So how to get the loads, right? You can use a very advanced computer, right? A very advanced computer with a very advanced software. And that technique is called the finite element analysis, right? In order to to use it effectively, you have to take a few more courses, right? Have to wait a few more years. Have courses on mechanics of materials, on advanced strength of materials, continuum mechanics, and course on actually the finite element method, right? And you'll be able to find these sort of results, right? In which, for example, you can tell the computer, okay, show me the most critical areas of this piece in red color. So you can see here that there is a bit of red there, giving you some information that is a critical area, and that perhaps the blue part is fine, right? So you have to add a bit more material here in the red part, or maybe increase the thickness of the piece, right? Maybe the loads you were carrying, right, were pushing this load, this body this way, and you fixed it right in the circle here, right? But anyway, it gives you an indication that that piece is working more than the other part, right? I am sure you have seen these simulations in YouTube, right, or in browsing some website, right? This comes from Mississippi State, and it's a simulation of a body, right? In this case, the body is a car, and there is a person inside. You see, it's a dummy, and you are applying a force which seems to be a trailer, right? And then it's exerting some forces on that car and bending the steel, and right, there is a lot of math and physics, and of course you have played video games, right? Video games have some of them really advanced in order to know if a piece is going to break or not when you shoot at it or whatever. You have to really know about the materials, right? So you are calculating internal forces, or there are this calculation of internal forces everywhere, right? Everywhere. And the things you use, your car, your even your toothbrush, has been designed to resist a certain load, right? So some people have gone and assumed some loads, calculated the internal forces, and based on the internal forces, they have come up with the dimensions of the things you use, right, day to day, like the size of a spoon, right, the thickness of a milk jug, all these things, all what you use in your everyday life has been designed by someone, right? And part of that design is the structural design, right? The thickness of a glass so it doesn't break, right? All this has to do with calculation of internal forces. So how can we calculate internal forces? Well, we're going to apply the method of sections, which we learned in trusses, right? In the context of trusses. Remember, we divided the truss into two pieces, and when we divided the truss, we uncovered the forces, right, in the two halves, and then we chose which half to analyze, and then we were able to calculate the internal force. So the first step, or the second step, is to slice the body into parts. With trusses, we saw that the method of sections was very efficient for determining internal forces of the truss elements, right? We really sliced the truss into two parts and exposed the internal forces, right? We can apply the same thinking here, right? That's the key. Once the rigid body is sliced and the internal forces are exposed, they can be treated as external forces. Well, this is for purposes of calculation. Remember that you were able to calculate reactions, no problem, right? Using your equilibrium equations. This is not going to be any different than that, right? We apply the principles of equilibrium to solve for the unknowns, right? So this is a rigid body. Here are the reactions in step number 2. And is subjected to a red force, right? An external load there. And the point is to slice it in the location in which you want to calculate the internal forces. So I'm going to slice it right there, right? Slice the body into two parts, and voila, right? I am seeing something, right? I am seeing something in step number 3. When I separated the two members, I am seeing something. There are 3 types of internal force that you have to remember, right? There is axial force, there is shear force, and there is moments, right? Now, axial force and shear force are the forces that we were using in the past, right? So forces we have seen and moments we have seen. So this is the point in which we realize that we have been learning about forces and moments because we were expecting the point in which we will slice a rigid body and we will find them again, right? We will find them again. So let me see. Let me see. Here, I'm going to use, what about I use blue color? No, green color. So once I exposed them, I saw that they are equal but opposite in direction, and that's required for equilibrium, right? Now, this guy is the axial load. This kind of rotational force here, that's the moment, of course. And this force here that is perpendicular to the axis of the body is the shear force. We'll define them in a minute, right? But these are the 3 types of forces you uncover once you slice a rigid body. Now, see how I drew them, right? For example, I'm looking at this half, and I'm going to kind of repeat that half here. The fact that I drew the internal forces going this way, the shear force, the axial load coming up like this, and the moment coming this way is no coincidence, right? I am following a convention of signs, and this is very important, right? We just to this is really important to use the right convention of signs. This is one of the most important things when dealing with internal forces, because things can go really wrong really fast if you don't use the right convention of signs, right? So more on this convention in just a minute, right? In just a minute. So what are the forces that I find, right? What about the axial force? Well, the axial force is directed along, or is it parallel to the member, right? Axial forces, we know, are or can be either in tension or compression. These forces make the body to stretch or compress, right? To stretch or compress, right? And then the convention is, if you have a piece, if it's sticking out, it's going to be positive, right? So that's a convention for tension force. Cables, for example, can develop only tension. A truss member, we saw that it could be tension or compression, right? Now, in the general case, a body can have axial forces, shear forces, and moment, right? A truss member could only carry tension or compression. What about the shear force? Shear forces are directed perpendicular to the member, right? When we deal with horizontal beams, right, horizontal beams such as this one, when we talk about shear forces, right, they right, when we break them, we slice them and we expose the halves, right? When they appear, right, you see them going up. Sorry, the convention is this. This goes down and this goes up. That's a positive sense of the shear forces, right? One going, let me see if I can erase this so it can be clear. Yeah, one goes up and down. Now, these shear forces, right? The point is to break things. When these forces are left to act, right, it will break your body, right, your rigid body, in a very critical way, right? So, if you left these forces to act, this body will break catastrophically, right? right? This will be the breakage that you will get, right? Suddenly, right? This will be the breakage that you will get, right? Shear forces are quite important, right? We try to avoid shear forces as much as we can, limit them in our beams, right? Because the failures they produce, right, when a certain rigid body fails in shear, it happens very, very fast, right? There is no time for people to get out of the way, right? The pieces just fall on people. Shear failures are quite catastrophic, right? Quite catastrophic. You can Google the Montreal overpass, right? Is it in Montreal? Yeah, Montreal overpass. I think it's called La Concorde. Right, and then so you can see what sort of failure you get, right, when things fail in shear. Just let me see actually. Let me see actually if you can find it, right? So you don't have to look it up. So Montreal overpass collapse. Yeah, you get that, right? La Concordia. You will get it when you search it this way. You will see what sort of failure you get, right? Essentially, it's a big piece of a highway bridge that just fell, just collapsed. Fortunately, there were no fatalities, right? But it just so sudden and so quick, right? So the shear force really makes things break in a really sudden manner, right? So when you are towing a trailer, right, you will have your car. I don't know how to draw cars, right? So this assembly, right, and you have your trailer here, right? It's carrying a forces in shear, right? So that could be a shear force. So what about the moment, right? What about the moments? Our old friends, a moment couple, right? Well, two types of moments can exist in a beam, right? Torque, that is rotation about an axis, right? And bending moment, right? So two types of moment. So torque, right? Torque is a moment about an axis, right? We have seen that disguised as moment about a line, right? For example, we see it in shafts for the automatic or the transmission of your car, right? You see this shaft turning, right? So that is the shaft is transmitting torque. The type of moment we are going to discuss in this part of the course is a different type of moment, right? Which makes a beam, right? This is a beam, right? The effects of that those moments on a beam, right, make it sag like this, or make it bend, right? It's the two words that you see, right? Bending moments make things bend. Bending moments or moments make things bend or sag, right? Depending on the sign, you could have deformation on the other, right? On the other direction. For example, this is a sagging moment. This is a hugging moment, right? Now, positive moment causes sagging, and then negative moment causes hugging, right? So these are the effects of moment. They tend to bend things, right? They tend to bend things. So convention for axial force, tension is stretching like this. Compression is actually shortening the member. For shear force, clockwise rotation will be positive, right? Counterclockwise rotation will be negative, right? The torque, right? Positive torque tries to rotate the body counterclockwise about an axis using the right hand rule, right? And bending moment, positive bending is caused by positive moment, cause a sag, a smiley face, and then negative bending created by negative moments cause a frown, right? The sagging and the hugging, right? These are the signs of the bending moment. And this is our very a very helpful friend that will allow us to remember this convention of signs, right? Now, myself, right, I particularly like to draw a small piece like this, and then I draw the shear like that, and I draw my axial force, and I know that my moment goes this way. So I always keep it with me, right? In my wallet, I have a picture of my wife and my kids, and then a picture of the convention of signs, right? That's what I carry in my wallet, right? There is no money in my wallet. There is just a card with a convention of signs, right? Convention of signs. So what are we going to do, right, to find these internal forces? We draw the free body diagram. That's the first step. And we go back to the first time that we presented the free body diagram. If we don't have a good free body diagram, we are not going to be successful in getting our forces, right? So free body diagram is so important. Second, we slice the free body into two sections, right? Normally at the location in which the internal forces are required. We identify and label the unknown internal forces following the convention, right? Following the convention of signs we presented, right? And we apply the equations of equilibrium. We have three, right? We have three. Sum of forces in x equal to 0, sum of forces in y equal to 0, sum of moments at a point equal to 0. And then we solve for the unknowns. And hopefully we have an equal number of equations than the number of unknowns, right? Now, in the next topic, we'll actually get to do our first example. So we are all excited about that. So see you on the next video.